So let us discuss the speed of transverse waves formed on a string. Okay, so let's suppose that we have some rigid support, okay, like this, and there is a string, okay, a string is connected to this rigid support. So there is a string connected to this rigid support, and there is some source of vibration on the other end. Okay, so maybe it might be a person that is vibrating that string, or it might be some other source. Okay, so there is some source of vibration at the other end, and because of that, waves are formed. Transverse waves are formed on the string, and so let's suppose these are the transverse waves. Okay, so there will be some speed of the transverse waves, right? So that speed will depend on two things. So first thing is the inertia of medium, okay, and the restoring force developed in the medium. Okay, so when you give a jerk to that string, what happens is you are applying some external force. Okay, you are applying some external force, right? So some restoring force is generated in that string. So the force that you are applying, it will be equal to the restoring force. Okay, so the string is vibrating because of what? The force that you are applying. Okay, that will be equal to the tension in the string. But there is something which opposes the vibration of the string. So which is that thing? It is the inertia of the medium, right? It is the inertia of the medium. Okay, so now inertia of medium is defined by mass. Okay, but now you can have strings of various lengths, right? So inertias of all those strings would be different. Okay, so how do we find the inertia? Okay, factor which decides the inertia, which determines the inertia of a string, it is not mass, it is mass per unit length. All right, see, there is the external force that you are applying. It will give vibrations to the string. These vibrations will travel through the string because of what? The internal restoring force that is generated, because one particle is connected to another particle, it is connected to another particle. So the tension that develops in the string, it gives rise to what? The transfer of energy from particle to particle. Okay, it's because of the bonds between the particles that energy gets transferred. Okay, so in this way, the speed of transverse waves that are produced in a string, it depends on the tension in the string. Okay, and there is one thing which opposes the vibration, it is the inertia of this medium. Okay, the medium is the string. So now see, now if we find out the formula for velocity of transverse waves on string, velocity will depend on, it depends on tension in the string. Okay, there will be some factor to which it depends. Okay, some power of this tension. Okay, so if we find out the formula, there will be some power of this tension that will come in the formula, and there will be some power of the mass per unit length. Okay, so suppose it is velocity is proportional to t raised to a and mu raised to b. Now we can guess, right? See, tension is the thing because of which the uh, the waves are traveling in the string. Okay, so it should be directly proportional to what? T to the power something, and mass per unit length, it determines the inertia of the string, so it should be inversely proportional to that, right? It would be some power, but it is resisting, right? Mass per unit length is the resisting quantity, okay, the opposing quantity. That's why it should be inversely proportional to some power of that. Okay, so we can solve this using dimensional analysis, and we'll get some constant, okay, some constant multiplied by square root of t divided by mu. Okay, if we solve it using dimensional analysis, and it turns out that this constant is equal to 1. Okay, so it turns out that this constant is equal to 1. So velocity of transverse waves on a string, they are equal to what? Sorry, it is equal to what? Square root of t by mu, where mu is equal to m upon L. M is mass of the string, L is length of the string, right? So the derivation of this formula is not there in our syllabus, okay? But we can find this using the dimensional analysis. So next is speed of longitudinal waves, okay? Speed of longitudinal waves in any medium. Okay. So see now, when longitudinal waves are formed in a medium, what happens? So some compressions and rarefactions are formed. Okay. So when there is a compression, the density of medium increases. When there is rarefaction, the density of medium decreases. Okay. So now see, the speed is equal to square root of elasticity of a medium divided by density. Okay, why so? See, the restoring force in a medium, or restoring stress you can say, when medium is subjected to some compressions and rarefactions, it is determined by the elasticity of medium. Okay, so as we discussed in transverse waves, so there is one thing, okay, the restoring force, which um, helps in traveling of the transverse waves in a medium. Okay, and there is an inertia factor, which is mass per unit length in this case, which opposes this traveling of waves, okay, which opposes vibration of particles. So here also there is some factor which helps in transfer of the energy, okay, it is the elasticity of medium, and there is some factor, the inertia factor in this case, it is rho, it's the density of a medium. Okay, so V is given by square root of E upon rho. V is given by what? Square root of E divided by rho. Okay, this is the formula for speed of longitudinal waves in a medium. So now question is, speed of sound, is it okay? So we have solids, we have liquids, and we have gases. Okay, so where is the speed more? Where the speed would be low? Where is speed greater? Where it is lower? What do you think? Gases and liquids, greater or lower? Solid will be lower. Okay. So see, if you just look at this formula, okay, and if you forget about the numerator, if you just look at the denominator, then density of gases is obviously lower, right? So you will say the velocity is inversely proportional to square root of rho. Okay, but it's not so. Density is lower, but elasticity of gases is also lower. Okay, elasticity of gases is also lower. The bulk modulus is also lower, right? Okay, so for solids, elasticity is much more, okay, compared to liquids and compared to gases. So the numerator is much bigger compared to what? The liquids and gases. So the velocity is greatest in solids. So velocity in solids is suppose Vs. Velocity of sound in liquid, sound or longitudinal waves in liquid is Vl. Velocity in gases is suppose Vg. So Vs is greatest. Okay, Vl is lower than that, and velocity in gases is even lower than that. Okay, so just for an example, velocity in gases is about 300 meters per second. It is of the order of 300 meters per second. Okay. Velocity in liquids is suppose some 1500 to 2000 meters per second. Okay. So let's take a number. Let's suppose it is 2000 meters per second. Okay. And velocity in solids. So it is about 5000 meters per second. Okay. Solids mean, what do you mean? What do I mean by solids? Is the metals. Okay. So velocity in solids is much more because their elasticity is much more compared to that of the liquids and gases. Everything clear? Okay, so please remember this. There can be a direct question based upon this thing. Okay, and then yeah. So for solids, the formula for velocity of sound or longitudinal waves. So velocity of sound in in solids, it is given by v equals to square root of y upon rho. Okay, so it will be Young's modulus. These all things we have to remember. And velocity of sound in liquids and gases, or let's call them fluids. Fluids, it is given by square root of bulk modulus divided by rho. Okay, it is given by square root of bulk modulus divided by rho. We have to memorize this thing. Okay, velocity of sound in solids, it is given by square root of y upon rho. In fluids, it is given by bulk modulus, square root of bulk modulus divided by rho. Okay. In early days, it was Newton, again Newton, who gave us the formula for the velocity of sound in fluids, okay, in gases. Okay. So let's see, I'm sorry, let's talk about the Newton's formula for velocity of sound in air. Okay. So see what happens is, there are compressions and rarefactions formed in air when the longitudinal waves, or we can say, so what, the sound travels in air, right? The compressions and rarefactions are formed. Okay. So according to Newton, when these compressions are formed, see, when compressions are formed, what will happen? So the particles of air, they will collide onto each other, we can say. So some heat is produced in the collision. Okay. And when there is rarefaction formed, this heat is, this heat goes to the surrounding, we can say. Okay. So in case of a compression, some heating is there. In case of rarefaction, some cooling is there. Okay. In case of compression, because of collisions of particles of air, there is some heating. And in case of rarefaction, there is some cooling. All right. So according to Newton, this heating and cooling in compressions and rarefactions, it is an isothermal process. Okay. So Newton argued, sorry, arg Newton argued in this way that, see, this compressions and rarefactions that are formed, this is a slow process. So that medium gets enough time such that when a compression is formed, the heat is given to the surrounding. When rarefaction is formed, the heat is taken from the surrounding. So surrounding will have some temperature. Okay, we know that the heat flows from higher temperature to lower temperature. Okay, so in case of compression, heat is produced. Okay, so this part of medium, it is heated, so the heat will flow to the surrounding. And in case of a rarefaction, what happens? There is cooling in this part. Okay, so it will take heat from the surrounding, and the temperature of this part of the medium will be equal to that of temperature of surrounding. Okay, so according to Newton, the heat produced in case of a compression and cooling happening in rarefactions is slow process. So the gets enough time medium gets enough time to exchange the heat with surrounding. Exchange meaning give and take. Okay, heat with surrounding, and the temperature remains constant. Okay, so in this way it is an isothermal process. Okay, so it is an isothermal process. All right, so now we have not studied these processes as yet. We'll study them in thermodynamics, but you might have studied this in chemistry also. Okay, so we'll just take a formula, right? So in case of isothermal process, the temperature remains constant. So you can write that PV is equal to nRT. Okay, PV is equal to nRT, right? So now if you differentiate this equation, what happens? So if you differentiate it, it is dP into V. The pressure is changing, volume is not changing, plus, okay, pressure, keep it constant, plus PdV. Okay, and if you differentiate right hand side, because temperature is constant, so right hand side is equal to 0. Okay, so now see, if you take this dP into V on the other side, you get PdV is equal to minus of dP into V. Now move dV on the other side, so you get P equals to minus of dP. The dV will come in denominator, and this V, I can take it into denominator of denominator. Okay, because it's in numerator. Okay, so it's the pressure in a medium is equal to what? The change in pressure minus of change in pressure divided by change in volume per unit volume. So what is this thing on the right hand side? It is the bulk modulus. Okay, it is the bulk modulus, right? So we can write that bulk modulus in this case is equal to the pressure. And then we get Newton's formula for velocity of sound in air. So velocity is just equal to what? Square root of bulk modulus divided by rho. Okay. So now bulk modulus is equal to pressure. So we can substitute that. So we get V is equal to square root of P upon rho. Got it? Yes, no? Is there any question? All right, good. So if you substitute the value of pressure and the value of density in this formula. So the speed that you get is nearly equal to, at normal temperature and pressure, it is nearly equal to 280 meters per second. Okay, this is the result of this formula. Okay, so from formula you get speed of about 280 meters per second, and if you do an experiment, so from experiment you get v equal to here about 330 meters per second. So what does this mean? There is some error in this formula. Okay, there is some error in this formula, right? So now see, thinking is nice, but it gives to an erroneous formula. All right. So this error was cleared by Laplace. So let's see Laplace's correction to the Newton's formula. Newton's formula for speed of sound in air. Okay. So what was Newton's assumption? That this process of compression and rarefaction, it's a slow process, so that what happens, the heat formed in a compression, it gets distributed to the surrounding, and there is some cooling in case of rarefaction. So that part of the medium, it takes the heat from surrounding to keep the temperature constant. Okay, now according to Laplace, this process is not slow. Compressions and rarefactions are formed at very high frequency. Okay, they are formed at very high frequency. That means very fast. Compressions and rarefactions, vibrations of the medium are very fast. And if vibrations are very fast, then this heat produced in the compression and the cooling that happens in case of rarefaction, it won't have enough time. Okay, so heat won't have enough time to get distributed to surrounding, and when the cooling happens, there is not enough time such that the medium will take heat from surrounding and the temperature will remain constant. So according to Laplace, it will not happen. It's not going to happen. Okay, so there is not enough time for the heat exchange between this part of the medium and the surrounding. Okay, so according to Laplace, heat is not exchanged. So this process is an adiabatic process. Okay, why? Because there is not enough time to exchange heat with the surrounding. Okay, so delta Q is equal to 0, and because there is no exchange of heat happening, this process is an adiabatic process. Okay, I'm sorry. So what happens in case of a adiabatic process? So in case of adiabatic process, PV raised to gamma remains constant. And what is this gamma? Gamma is the ratio of specific heat capacities at constant pressure to specific heat capacity at a constant volume. Okay, gamma is the ratio of specific heat capacity of a medium at a constant pressure to specific heat capacity at constant volume. All right. So in case of adiabatic process, PV raised to gamma remains constant. So now let's differentiate this thing. So if we differentiate this thing, what do we get? dP multiplied by V raised to gamma as it is, plus P as it is, multiplied by, now this is V raised to gamma. So if you take its derivative, if you differentiate it, you will get gamma multiplied by v raised to gamma minus 1 multiplied by dv. Okay, if you differentiate with respect to v, and on right hand side you have a constant, so this is equal to 0. Got it? So then you can take v raised to gamma minus 1 common between these two. So if you do that, if you divide by v raised to gamma minus 1, this v raised to gamma can be written as v raised to 1 multiplied by v raised to gamma minus 1. So if you cancel out v raised to gamma minus 1, a v will remain there. Okay. So ultimately what do you get? You get dp multiplied by v plus you have p multiplied by gamma into dv. This is equal to 0. So again you take this on other side, right? You take this on other side. So you get gamma times p dv is equal to minus of dp into v. Okay, and then you divide by dv. So what do you get? Gamma times p is equal to minus dp upon dv upon v. Okay, so this is the bulk modulus. So now bulk modulus is not equal to pressure. It is equal to gamma times the pressure. Okay, it is equal to what? Gamma times the pressure. So bulk modulus for adiabatic process is equal to gamma times pressure. All right. So then you can substitute this. You can substitute this in the formula for velocity, and then you get velocity is equal to square root of gamma times p divided by rho. Okay. So you got this? Yes, no? Okay. Then if you substitute the value of gamma, that is Cp by Cv, and pressure and rho. Okay, if you substitute all that, what do you get? You get the speed of sound in air is equal to 330 something. Okay, let's consider 330 meters per second. So this formula matches with the experiments. That means this formula is correct. Okay, so this is the Laplace's correction to the Newton's formula. So which formula do we need to remember? We need to remember this formula, not the Newton's formula. Is it clear? If there is any doubt, you can ask me. All right, good. So then, see, what are the factors on which the speed of sound in air will depend? Okay, so factors affecting speed of sound. So see, this V is equal to gamma times P divided by rho. Okay, now density can be written as what? Mass upon volume. Okay, so if you take molar mass, the volume will be the volume of 1 mole, right? So you will get V equals to square root of gamma multiplied by P divided by m upon V. Okay, m is molar mass, V is volume of 1 mole. Take that V in numerator. What do you get? So it is gamma multiplied by PV divided by m. And what is PV? PV is equal to, I'm sorry, PV is equal to nRT. Okay, so you get this formula, gamma times RT upon M, because N is equal to 1. I have taken 1 mole, right? So R is constant, M is constant. Okay, if you take a specific gas, then its molar mass will remain constant. The ratio of specific heat capacity at constant pressure to constant volume, it depends on type of gas. So it is also a constant. So V is directly proportional to what? Root of T, temperature. Okay. What is T? It's the absolute temperature. It's not temperature in degrees Celsius. What is SI unit of the temperature? It's Kelvin, right? So V is directly proportional to root of T. Okay. So if temperature increases, what will happen? The speed of sound in air will increase. We have this formula. So if you take this formula, V equals to square root of gamma times P divided by rho. So you will think that if pressure changes, the speed of sound will change. Okay, so V is directly proportional to root of P. But see, when pressure changes, density also changes, right? When pressure increases, there is increment in density. Okay, when pressure decreases, there is decrement in density, right? Mm. Okay, if there is more pressure, density will increase. If there is less pressure, density will decrease. Okay, so now the change in pressure and change in the density, they are linearly proportional. Okay, so there is no effect of the change in pressure on the speed of sound if the temperature remains constant. Okay, because see, we can substitute for density. Density is equal to mass upon volume. If you take 1 mole, then it's molar mass divided by volume of 1 mole. Take that V in numerator, so you get RT, right? PV is equal to RT. So from there we get what? All other things are constant. V is directly proportional to square root of T. Okay, so if pressure changes and there is no change in temperature, then what will happen? The speed will remain constant. So the speed of sound, speed is independent of pressure if temperature remains constant. Okay. So you just take it as the speed of sound is independent of pressure. All right. So this is second thing. Then there is one more thing, humidity. Okay. What is humidity? It's the amount of moisture present in the air. So if there is more moisture, what will happen? The density of air will decrease. Okay. If humidity increases, the density will decrease. And if the density decreases, then what will happen? The speed will increase, right? Yes, no? Okay. So this is another factor, humidity. All right. So the speed of sound increases with humidity. All right. And then it depends on some other factors like if wind is blowing or not. Okay. So if wind is blowing, there will be some change in the speed of sound. Okay. But those factors actually, okay, those are random things, right? So there will be some change. Okay. So what kind of change depends on, it depends on the specific situation itself. Okay, all right. So let us see some problems. Okay, good. So let us see some problems based upon these topics. Mm. So first problem, the velocity of sound in any gas depends upon option A, wavelength of the sound only, option B, density and elasticity of gas, option C, intensity of sound only, option D, the amplitude and frequency of sound. Tell me. Option B, right. It's density and elasticity of the gas. Okay. Next one. If the amplitude of sound is doubled and frequency reduced to one fourth, the intensity of sound at the same point will be. So, okay. So we haven't seen the intensity. Okay. So let's discuss intensity in short. So what is intensity of a wave? So intensity is amount of energy carried by wave per unit area per unit time. Okay, it's the amount of energy per unit area per unit time, right? So the energy is directly proportional to, you can say, sorry, the intensity is directly proportional to energy. Okay, so the intensity, let's denote it by I, it's directly proportional to energy. So what is energy of vibrations? We know that energy of vibrations, it is directly proportional to, okay, it is half of m omega square a square, right? This is the energy of vibrations. And intensity is energy carried by wave per unit area per unit time. Okay, so see what is happening here. Amplitude is doubled, so A is doubled and frequency is reduced to one fourth. Frequency is reduced to one fourth. Omega is reduced to one fourth. What will happen? So this is one fourth to the power 2, because frequency or angular frequency, you can say, it is reduced by the factor of one fourth, and amplitude is doubled, so 2 to the power 2. Okay, so it is 4. 2 to the power 2 is 4, and divided by, you have 1 upon 4 square, so the 1 4 will get cancelled. So what will happen? 1 by 4 will remain. Okay, so it decreases by the factor of 4. Option C is the answer. Okay, very good, Sanjay. Got it? Okay. 5.5 meter length of string has a mass of 0.035 kg. If the tension in the string is is 77 newtons, the speed of wave on the string is. So we know speed of a transverse wave on string, it is equal to what? Square root of t upon mu. And what is mu? It is mass per unit length. So length is given, mass is given. That means we have to substitute mu equals to m upon L. So, okay, so it is T upon m divided by L. So divided by, so L is in denominator of denominator. That means this goes to the numerator. So this is simple question, straightforward. Let's substitute the values. So T is equal to 77, sorry. Then L is 5.5, and in denominator you have 0.035. So let's make it 35 multiplied by 10 raised to minus 3, right? So it's equal to, yeah, so we can divide by 7, so 5 will remain there. So numerator will have 77 divided by 7 is 11 upon this 5, and you have 5.5. Okay, or let's make it 55 multiplied by 10 raised to minus 1. Okay, let's take this 10 raised to minus 3 in numerator, so it becomes 10 raised to plus 3. Plus 3 minus 1 is 2. So 10 raised to 2. And if we divide this by 5, it is 11. Okay, so we have got 11 square multiplied by 10 square in numerator. Square root will be 11 multiplied by 10. So 110 is the answer, right? Option A. Oh, you are faster than me. Right. Okay, so let's move on to the next question. Velocity of sound waves in air is 330 meters per second. For a particular sound wave in air, a path difference of 40 centimeters is equivalent to phase difference of 1.6 pi. Then the frequency of the wave is. So this is like the earlier questions that we have solved. Okay, so phase difference is given by what? 2 pi x divided by lambda. So we can find out lambda from here. It is 2 pi x divided by theta, right? So x is given, phase is given. Okay, let's substitute that. It is 2 pi multiplied by x is 40 centimeters. So it is 40 multiplied by 10 raised to minus 2 meters. Divided by theta is 1.6 pi. Okay, or let's write 16 pi multiplied by 10 raised to minus 1. So pi and pi gets cancelled. Then you have, if you divide by this 2, it's 8. And then 40 by 8 is 5. You get lambda equals to 5 multiplied by 10 raised to minus 2 plus 1. So 0.5. Right. So lambda equals to 0.5 meters. And speed is given. It's 330 meters per second. Okay. And you want frequency. So n is equal to v upon lambda. That is 330 divided by 0.5. So it is 660 hertz. Let's see next question. The temperature at which the speed of sound becomes double as was at 27 degrees Celsius is. So first of all, we know speed is directly proportional to root of T, temperature. Okay. So V2 upon V1 we can say. Final temperature is T2, initial temperature is T1 is equal to square root of T2 upon T1 because V is directly proportional to root of T. But problem is we cannot take 27 degrees Celsius as it is, right? We have to convert it into kelvins. Okay, so T2 divided by T1. T1 is what? So it is 27 degrees Celsius. Convert it into kelvins. We have to add 273. So it is 300 kelvins, right? And how much is V2 by V1? So it gets doubled. So V2 by V1 is 2. So let's square it. So we get 4 equals to 4 times 300 we can say is equal to T2. Okay, that is 1200 is T2. T2 is equal to 1200 kelvins. And options are in degrees Celsius, so we have to subtract 273 degrees, right? So subtracting 273 from this, it will be 927. Option C. Hospital uses an ultrasonic scanner to locate tumors in a tissue. Okay, so the thing of your interest, right? Okay, you want to be doctors, right? A hospital uses an ultrasonic scanner to locate tumors in a tissue. The operating frequency of the scanner is 4.2 meters, sorry, not meters, megahertz. Okay, it is megahertz. I'm sorry. Okay, The speed of sound in a tissue is 1.7 kilometers per second. The wavelength in the tissue is close to. So this is very, very simple. Frequency is given, speed is given, and you want wavelength. So lambda equals to just v divided by n, right? So this is just calculation. 1.7 kilometers per second converted to meters. So it is 1.7 into 10 raised to 3 divided by 4.2 multiplied by 10 raised to 6. Because it is megahertz, we have to convert it to hertz. So if you take this into numerator, this will become 10 raised to 3 minus 6, 10 raised to minus 3. But then you have to find 1.7 upon 4.2. So, okay, 10 raised to minus 3 is there, multiplied by 10 raised to minus 3. So this will be close to, uh, it will be less than 5, right? Because 2 upon 4 will be 5. So this thing will be less than 5. You can say it is near about this thing, option A. Right. Let's move on to next question. A transverse wave is represented by the equation y equals to y naught sine of 2 pi upon lambda vt minus x. For what value of lambda is the maximum particle velocity equal to 2 times the wave velocity? So we have solved these kind of questions, right? So maximum particle velocity V max is equal to what? 2 times of the wave velocity, 2 times of n lambda. V max of particle, right? So what is maximum particle velocity? It is a omega. Particles vibrate and the maximum velocity with which they can vibrate is at the mean position. It is equal to a omega. So a omega is equal to 2 times of n lambda. Okay, it's not a, the amplitude here is y naught. Okay, so let's take y naught into omega. This 2 pi, sorry, 2 times n lambda. Okay, and omega can be written as what? 2 pi n. So let's write y naught multiplied by 2 pi n is equal to n lambda. N gets cancelled, 2 gets cancelled. Okay, so lambda equals to y naught into pi is the answer. Option D. Clear? Okay, good. Next question. The equation of wave is represented by, this is the equation, 10 raised to minus 4 sine of 100 t minus x divided by 10 meters. Then the velocity of wave will be. Okay. So again you have to find out what? The n and lambda. So compare this with y equals to a sine of, because we have t here, so it's omega t, or you can say 2 pi nt minus 2 pi x divided by lambda. Nt minus kx, k is 2 pi by lambda. Okay, compare with this, you get 2 pi n, or let's write, okay, so 2 pi n is equal to 100. So n is equal to 100 upon 2 pi, and 2 pi by lambda is equal to 1 upon 10, right? So lambda equals to 10 times 2 pi. Okay, so what will be n lambda? N lambda, v is equal to n lambda, that is equal to 100 upon 2 pi multiplied by 10 into 2 pi. So this 2 pi and this 2 pi gets cancelled. So it is 1000 meters per second. Yeah, it's option C. So there is another way to solve this. Okay, so instead of considering this equation, we can just consider y equals to a sine of omega t minus kx. So that way it will be simpler. And if we remember, v equals to omega upon k. Okay, So omega is just 100, and how much would be k? So k is 1 upon 10, right? So 100 upon 1 upon 10. That 10 is in denominator of denominator, it goes to numerator. It will be 1000. So if we remember this relation, v equals to v equals to omega upon k, and y equals to a sine of omega t minus kx, then it will be faster. Point source emits sound equally in all directions. In a non-absorbing medium, 2 points P and Q are at distance of 2 meters and 3 meters respectively from the source. The ratio of intensities of waves at P and Q is. So as we discussed, intensity falls off inversely as r square. Okay. So what will be ratio at 2 and 3 meters? So intensity is inversely proportional to r square. So you can say I1 upon I2 will be equal to R2 upon R1 square, because it is inversely proportional to R square. So substitute R2 and R1. R2 is 3, R1 is 2. So you get 3 upon 2 square, that is 9 is to 4. Option C. Transverse wave propagating along x-axis is represented by 8 sine of this thing minus this thing minus this thing, okay, where x is in meters and t is in seconds. The speed of the wave is. This is simple again, okay, repeated kind of questions. So we can say 2 pi x upon lambda, okay, this will equate to 2 pi x upon lambda. So 2 pi x upon lambda is 0.5 pi x, okay, x gets cancelled, pi and pi gets cancelled, so lambda is equal to what? 2 divided by 0.4, that 0.5, that is lambda is equal to 4 meters, right? And 2 pi nt is equal to 4 pi t. So once again t gets cancelled, pi and pi gets cancelled, n is equal to 4 upon 2. So n is equal to 2 hertz. Okay, so v equals to n lambda 2 times 4. Okay, that is 8 meters per second. So let's see next question. See, we had seen some questions like this earlier also, but these kind of questions are repeated many times. Okay, so a transverse wave is represented by y equals to a sine omega t minus kx. For what value of wavelength is the wave velocity equal to maximum particle velocity? Wave velocity is equal to maximum particle velocity. So again, a omega is the maximum particle velocity. It's equal to n lambda. Okay, or you can say n is equal to omega upon 2 pi, right? So omega and omega gets cancelled, take that 2 pi on other side. So lambda equals to 2 pi multiplied by a. Option C. So this question is repeated many times, right? Sometimes particle velocity, maximum particle velocity is equal to wave velocity. Sometimes it is 2 times that of wave velocity. Okay, but it's one and same thing, right? So this is simple. Let's see next question. Sound waves travel at 350 meters per second through a warm air and 3500 meters per second through brass. Okay, through brass, that is solid. Wavelength of 700 hertz acoustic wave as it enters brass from warm air. Okay, so see what happens when any wave travels from one medium to another medium. Its frequency remains constant and it's the wavelength that changes. Okay, so reason for that is the source is performing some vibrations, Okay, it is producing that wave at a particular frequency, right? So number of vibrations per unit time, it is defined by source. Okay, so number of vibrations of medium per unit time is defined by source. Okay, and wavelength is the property of the medium. Wavelength is property of medium. How much that medium allows that that wave to spread. It is defined by the medium. Okay, so frequency is constant. Wavelength will change from medium to medium. So first we have to find out the first we have to find out wavelength. Okay, so V2 upon V1 is equal to n times lambda 2 by lambda 1. So what is the ratio of speeds? It is 3500 by 350. So 3500 divided by 350 is lambda 2 by lambda 1. Okay, so that is 10. So this is equal to 10. And then we have to find out wavelength lambda 1. Okay, actually we have to find out wavelength in the other medium. So first let's find out wavelength in first medium. So lambda 1 is equal to V1 divided by n. So this 350 divided by 700. So it's 1 by 2. Okay, and when it goes to other medium, what happens? Wavelength increases. It becomes 10 times. So it is lambda 2 is equal to 1 by 2 multiplied by 10. Oh, the question is only, oh, I'm sorry. I was finding the wavelength. It just increases by the factor of 10, right? This thing is not needed. Volume of 1 mole is 22.4. Okay. So it's given that 4 gram of gas occupies 4 gram of gas occupies 22.4 liters at NTP. Okay. The specific heat capacity of the gas at constant volume is 5 joule per Kelvin per mole. Okay. So CV is given, specific heat capacity at constant volume is 5 joules per Kelvin per mole. If the speed of sound in gas at NTP is 952 meters per second, so V is given 952 meters per second, then the heat capacity at constant pressure is heat capacity at constant pressure. Cp is asked. So we know V is equal to what? It is gamma times RT upon M, right? Gamma times RT upon M. So why am I using this formula? Because rho is not given, density is not given, okay, and it's NTP. So the temperature at NTP is 300 kelvins. Okay, so this is molar mass. This is given 4 grams. R is given 8.3. Okay, and gamma is equal to Cp by Cv. So V is also given. So V equals to Cp upon Cv multiplied by RT 8.3, or let's write it as RT divided by M, like this only. And then let's calculate this. Okay, so let's take square. So it will be V square. V square equals to Cp upon Cv multiplied by RT by M. Okay, so we want Cp. So let's take other things on other side. So Cp is equal to V square Cv multiplied by M divided by RT. Oh, it is very lengthy calculation. Okay. All right. It is very lengthy calculation. So V square 952 Let's try to do some approximation. CV is 5, M is 4 multiplied by 10 raised to minus 3. This is 8.3 multiplied by temperature is 300. Okay, so 5 fours are 20. 20, still it is. Okay, so let's take a page. 952 square. I will approximate this with 1000. Okay, so I'm increasing numerator a little bit, so I will increase the denominator also. So let's do round figure. Okay, so this is 20 multiplied by 1000 square, so 10 raised to 3 square, and here you have 10 raised to minus 3, so it will be 10 raised to 3 divided by 8.3. So I have increased this, I will increase this also to 10. Okay, so 10 multiplied by 300, so it is 2 by 3 multiplied by 10 raised to 1, right? If I take this, or 20 by 3, so is it 6.6? CP is 6.6. Yeah. Oh, I'm sorry, the options are closed. So will it be 7 or something? Can you calculate? I guess it will be close to 7. Option A. I think this kind of question they should not give because options are closed. Okay. Okay, take it. Is it option A? Okay, good. All right. Okay, so these kind of questions I think they should not give because it's a lengthy calculation, but what can we do? All right. Let's see next question. A uniform rope of length L and mass m1 hangs vertically from rigid support. So you have a uniform rope like this. It has mass m1 and length L. A block of mass m2 is attached to the free end of the rope. So there is block of mass m2 which is attached. A transverse pulse of length lambda1 is produced at the lower end of the rope. The wavelength of the pulse when it reaches the top of the rope is lambda2. The ratio of lambda2 by lambda1 is. Okay. So yeah, this is a simple question. See, we know V is equal to, okay, V is equal to what? Square root of T upon mu. Okay. So this transverse pulse, it gets produced here. Okay. So what will be tension at this point? Tension at this point will be equal to what? How much is the weight hanging from that point? It's m2 into g. So tension at this point is just m2 into g, right? Okay. And then when it reaches here, so the tension here will be much more. Okay, it will be weight of this part plus this part. Okay, so it is m1 plus m2 multiplied by g. So it's because of the tension, the difference in tension at two parts. Okay, the velocity will change. So you want lambda2 by lambda1. So v2 is square root of t2 by mu. V1 will be equal to square root of t1 upon mu. So mass per unit length of the string will not change. So we can cancel it out. Okay, V2 will be equal to what? Square root of T2 upon mu. right? So then V2 by V1 is, I can say this as it is n lambda 2 upon n lambda 1, and we had discussed that n remains constant. It is the property of source. Okay, so n doesn't change, it's the wavelength that changes. Okay, so this is equal to square root of T2 upon T1. And what is T2? It is M1 plus M2 multiplied by G. Okay, because uh, when the wave reaches at this point, it has to, the string has to support its mass and this mass. Okay, so tension in the string will be equal to this plus this weight, total weight, okay, at the top. So it is M1 plus M2 into G, and in denominator you will have M1 into G. So G will get cancelled, okay, N gets cancelled. So lambda 2 upon lambda 1 is equal to M1 plus M, sorry, root of M1 plus M2 divided by MO. I wrote, yeah, this is correct. I wrote M1 here. It should be M2, right? Okay, because the weight that is hanging from this part, it is M2, not M1. Okay, so it is option D.